Hi there, welcome back to the channel. Welcome to the start of a new restoration project. It's a tube radio this time, and it is a Grundig 2447 from around 1965. So near the end of the tube era, and this one is one I've been looking forward to working on because I have the two predecessors sitting at the back there, the two 147s. Those are identical except in looks. And I wanted the later version, which has quite a few changes. I was keen to see what the changes were. And the condition of this radio promised to be quite a nice project. Well, I'm not saying it's not going to be a nice project, but it did come with a few hidden features, hidden mess-ups. Somebody's been in here and done some real damage. And of course, I only found out once I opened it up. So in this case, beauty was skin deep. And in this, the first video in the series, it's going to be a short series, but in this, the first video, I came across a really strange problem with the audio. And unfortunately, the problem was me. So I had a pretty tough time finding a problem on this, and it was all to do with my stupidity. But that's part of the video. And if you want to see how someone can make some stupid mistakes after restoring over 100 radios, stick around and enjoy the video. But first, I'd like to thank the sponsors of the video, PCBWay. You'll find them at PCBWay.com. They've supplied all the PCBs that I've used in my projects, as well as some 3D printing designs that I've developed. Most of these have been made available in the share section of the website, where you'll find thousands of community shared designs that you can order directly for your own builds. I've always found them to be fast, reliable, and exceptionally high quality, and the enormous range of services they offer will definitely assist you with every aspect of your design, including PCB assembly, if that's what you desire. Right now they're running the PCBWay Christmas Big Sales, where you save up to 50% and you can get free coupons, as well as many, many other goodies that you can take advantage of during this holiday season. So do yourself a favor, go to PCBWay.com. I'm sure you'll find something for your needs. I really love this style of radio. These came out in the 60s at the end of the tube era. This one is the Grundig 2447, and it is one of a series of radios that adopted this look, the more streamlined, more modern, more minimalistic look. The enclosures aren't as boxy as they used to be, and they actually fit really nicely in a modern environment. And as proof of my obsession, here are two more. Yeah, why do you do one when you can have three? These are both Grundig 2147s. They came out at the same time, and the one is walnut and the one is teak. And quite honestly, I think this is walnut and this one's teak. I can't really tell the difference, but I fell in love with these two and I bought the two of them together and restored them. And I really love the way they match each other. I've even considered putting Bluetooth receivers on these and have the left channel go to one, the right channel go to the other when I send music from Bluetooth. But this one over here was actually the subject of a restoration series that I did for the ELV magazine. It's a German electronics magazine. It was done over, I think, 22 months. They really wanted a lot of details. So every episode or every article, which was bi-monthly, would go into one section of the restoration in great depth. And strangely enough, I don't speak German, so this was written in English and they would kindly translate all the articles for me. So I've actually got a series of articles in a German magazine that I cannot actually read myself. Anyway, these guys came just before this one. This one is 1965 to 1967. And the 2147s on the left there were 1961 to 1964. So this one is slightly more modern, and it really is even further away from the tubes. So it's closer to the end of the tube era than those two, which leaves me even more curious to see how they've done this inside. I've checked the tube lineup. There are a few differences. I know, for example, that for the FM detection, and I believe maybe even the AM detection, they've used germanium diodes. But I'm really looking forward to opening this up and working on this one and adding this to the collection of its two older brothers over there. So let's have a closer look at this guy. Now with the piano keys, we've got off, bass and disc. I'm not sure what that means. TA will be the external input, long wave, medium wave, and then shortwave. But it's not the full shortwave band like the previous two versions that I showed you. This is only the 49-meter band, and it says Luxembourg. I'm sure there's a story there, can't remember what it is, but you can tell me in the comments. And of course, FM. The dial glass is complete and in perfect condition, and the FM goes to 104 megahertz. Brilliant. The other two that I showed you only went to 100, which means my favorite station at 101.6 will be reachable without any shenanigans. Good. And here we've got the volume control, which is turning smoothly, the tone control, which is turning smoothly, and the tuning, which, oh dear, looks like the dial string is broken and it's just scraping inside there. Something is wrong. As for the cabinet, well, the front, it's in pretty good condition. Other than that one nick over there in the veneer, we can fix that. Other than that, it's looking pretty good. The top here is much more faded, and there is quite a big stain over there, but it shouldn't be an issue. These are pretty easy to restore. The back looks like it's in immaculate condition. Everything seems to be fine. There are no breaks, no tears. This is looking really good. We've got the output for a 5 ohm loudspeaker, external speaker over there. The mains voltage selection is achieved not with a switch, but by putting the fuse in the respective holder for the different voltages. That's quite normal with these radios. And over here we've got the input mono tape. What is this? Tonabnehmer. This is the tape in and out, which can also be used for Bluetooth input or phono input, I guess. The tube selection, we've got the tubes are quite usual except the last one. Actually, that one's also not too usual. EAF 801. And it's also got the ECL 86, which is a tube that I do like. It acts as preamp and power amp in one. And then we've got the antenna sockets, the dipole input at the top and at the bottom for the AM antenna. The condition of this back panel is immaculate. I'm going to get everything out of here so we can look at what we're facing. Well, folks, we have a bit of a mess here. Yeah, this is going to be a bit challenging because these are the speaker wires I cut. That's not a problem. But there's no tuning condenser. Somebody has removed the tuning condenser. This is what I find where you'd normally find a tuning condenser. In fact, you would normally find the condenser on the right-hand side, right by the tuning control, but this one is on the other end and there are a lot of pulleys around here, which makes this quite a challenge. The 3 wires to the condenser are here. That's not a problem, but I'm going to have to find one to fit in here somewhere. These are the brackets that hold it up. And then there's going to be all the dial cords that have to go all over the place. And they sent me, very kindly, this inside a plastic bag. So somebody, bloody hell, why would they do that? Somebody ripped this out for something else and has just made this a rather more interesting project, I must admit. But let's take this one step at a time. Normally, that would be there and that would be there because the tuning dial is, or the tuning control is at the front there. So they've put it in opposite ends. I don't know why. This is completely different. This interior is completely different to the 2147, but it should still work the same way, and it will work the same way. And I'm just having a closer look here. There are the fuses that have been removed. So obviously this hasn't been powered for some time. We've got the power transformer over here. We've got the output power tube on here. This one is the one that has the preamp. It's got a triode and a pentode in one. I like these tubes. We've got the filter cap over there. That'll probably be the ECH81 mixer oscillator, the 2 IF transformers. All that is normal so far. This is obviously on a PC board, which may make getting to the components a little easier or not, as the case may be. We shall see. Here's our FM front end with ECC85 on there. Here's the gaping hole where the tuning condenser would be. This is going to be fun. Let's look on the underside. So as expected, under the switches, we have all the RF stage, and those are fairly standard. Should be easy to get to them. And then on this side, we've got the magic eye down here, and we've got the rest of the circuitry under the cobwebs. I see they've got a pulley down here, so these cables, or rather the dial cord, goes under here, goes through a pulley over here, goes to the top side, and then does all the magic with the condensers. So yeah, this is going to be fun. Where the hell do I start? I'm going to tackle this exactly the same way that I tackle all my projects. I'm going to go power supply first, then the audio stage, then the radio stages. Okay? So what's the first step? Power supply, see where the mains is coming from, make sure it's getting in there, make sure that it's going to the selenium rectifier, going through the transformer, make sure the transformer is fine. Filter capacitor over there, probably have to restuff that one. It's going to be dead by now. And then once I've got the power supply sorted out and I've checked where all the B plus is supposed to go to, make sure it's getting there, then I can focus on the audio stage, make sure that audio going into the external input, the tape input, can get through to the speakers. So we do all the tone shaping, the power stage, the preamp stage. We'll have to check if this tube is fine, because this tube is actually doing all of that. And then I'll worry about the radio, because I know that I can solve this. The advantage of being a bit of a hoarder is I've got a few of these condensers lying around, and I'm sure that I can Frankenstein something in there and make it work. What a shame. What a shame. Oh well, you have to deal with what you have, and that's what I'm going to do. I also noticed a bit of rust on some of these parts. Some of the metal, the screws, the actual transformer over there, there is rust on there. So I've got quite a bit of cleaning of the chassis to do as well before I even bother worrying about the missing tuning condenser and trying to figure out where this light goes. No idea. Oh well, this one should be interesting. I probably have to thank the butcher that did that, because that does make the project a little bit more challenging. And I always look for a challenge on these things, and I think I found it. Okay, let me get started. Well, folks, a lot has happened here. As you can probably tell, I have been quite busy. I did my usual test of the power transformer using the low voltage method. Now, all these methods are best described in my Back to Basics series, and I'll link those below. It just avoids me explaining everything again. And in the Back to Basics videos, I go into a lot more detail. So once I determined that the transformer was fine, I needed to restuff or replace the filter capacitors. And as you can see, I opted to put them on there. They were soldered onto the board, which made it a lot easier. That particular filter cap had two 47 or 50 microfarad capacitors and one 8 microfarad. So I've replaced that with two 47s and one, 10 microfarads? Yeah, that's it. And then I just got sick of seeing the dirt, so I decided to give this whole thing a clean up. And that was done with my airbrush compressor, lots of isopropyl alcohol and a brush, and it looks pretty good. Everything looks pretty clean. And once I got started with the cleaning, I couldn't stop. I did the entire radio, top to bottom. That cream faceplate needed a few touch-ups. So I used artist's acrylic paint, which dries very quickly and it's very clean. It's water-based, so quite easy to work with. Those knobs look absolutely new. I also found where the second light bulb went. So with everything cleaned up and the filter capacitors replaced, I then did my usual checks for continuity. I wanted to make sure that the B plus is getting to where it's supposed to. And again, I'll show how that's done in the Back to Basics series. And with this particular layout on a PC board, it's very, very easy to trace. Let me show you what it looks like on the schematic. We've got the entire schematic. I found a very good surface manual for this. This is actually for 3 models. We're interested in this one. Now, bear in mind, when you look at these schematics, sometimes there are small differences between the different series, but never mind. If we find something that doesn't really match our schematic, we'll certainly notice it. And this is what I've done so far. I've started with the power supply as usual. And as you can see, all I did is check continuity from here to there. I've put in the fuse, so I'll mark that as red because it's a replacement part. And then the secondary is coming out here. And I have not powered this thing up yet, but I've checked continuity all the way through. So we see that the B plus, which comes out at this point, goes to the first filter capacitor. That's one of those capacitors inside that 3-section cap. It's given us capacitor 61, 50 microfarads. Then it goes into the output transformer as usual, through the primary of the output transformer, and it gets to the anode of the pentode part of this tube. This is the ECL86. It has a pentode and a triode. So this tube sort of self-preamplifies. This part acts as a preamplifier for the audio. This acts as the power amplifier for the audio. That's why I like this tube. I really love it. Difficult to get, but I love it. Anyway, once we've checked that, we can mark that in green. And if we take it from here, it also goes through a small part of the output transformer as well, which sort of acts as a hum reducer. And it goes through a 1.3K resistor. And what I did is I took it from there, I put the multimeter on there, and I measured resistance to this point, and I got a few ohms. I think it was about 12 ohms. And then when I measure to this point, I get 1.3 plus 12 ohms. This resistor is spot on, absolutely spot on. By the way, this indicator here, this symbol, indicates a wire wound resistor. And in fact, they actually show us down here, draadwiderstand, a wire wound resistor. These are the normal resistors. They've got different symbols depending on their power rating. So you can look at a resistor like that one there, and it looks like that one, so it's 1/3 watt. Anyway, that's just a by the way. So it comes through here and it goes to the screen grid of the pentode, so pin 3. So you literally measure from here, resistance all the way through to pin 3, and you get 1.3 something K. So you know that this resistor is fine and continuity is fine. You also then take it to the second capacitor, which was the one that was replaced as well. And you've got a second B plus over here. That screen voltage, I call it B2 plus, and it goes somewhere else. So you leave your multimeter, for example, on the leg of the capacitor, and you measure wherever it goes. So it goes that way. We'll stop there. It goes up here, goes through a 2.2K resistor. It goes up here. Let's follow that path first. It goes to there. It doesn't go through the capacitor, but it actually goes through that coil, which is a very small resistance. Goes up here through another coil, and it goes to the anode of the EAF 801. So if you measure the resistance from this point to that point, what would you expect to find? You expect to find a few ohms over here, another few ohms over here, 2.2K. So it really is something in the order of 2.2K, and that's exactly what I measured, 2.2 something K, which tells me this line is perfectly fine and that resistor is good. The other place you can measure, you've got to follow the line everywhere it goes. Remember, it goes through coils and resistors, it does not go through capacitors. So from here, we take the same path up there, through that resistor, so 2.2K. It gets to here and it goes that way as well. And it goes to pin 1 of the EAF 801. And what resistance do you expect? You expect 68K plus 2.2K. So you expect 70.2K. And I got damn close. These resistors are very, very close. Very, very close to the rated values. So I marked that as green as well. Then we've got another path for that B+, and that is through that switch over there. That is the 6M and N. So if we look at the switching, there's our switch, and we go for 6. 6 is over here. It's on the PA or TA switch. M and N, there's M and N. So when the pickup is off, the L and M is connected, so M and N is not connected, which means that when we've got radio selected, for example, this will be made. This will be a closed switch. And that means that that B2 plus should also get to pin 6 of the magic eye. And between pin 6 and 9, you should measure 100K, which I did. And then it goes on to here. And here we've got another situation. If what is that? 13G, 13GHI. Where is 13? Go to 13. 13 is FM. GHI, so it's this trio over here. And you flick between FM and one of the medium wave band, one of the AM bands, and you will see that what happens is that when FM is selected, this section is switched off, but never mind. They switch off the oscillator section on the AM bands for the AM bands when you select FM. But then never mind, you just flick around and make sure that you find this resistance in one place. And what do you find? There's B2 plus through there, 33K to pin 8 of the ECH81, and that was fine. This one here, 39K to pin 1 of the ECH81, that was also fine. Then you select FM, and that goes that way. And the B2 plus comes through another set of resistors through 1K, and there's the other path. Plus 15 is 16K, plus a few ohms to pin 6 of the ECC85, so that was also fine. And from here, you've got another path, so you've got 1K in line there, and you've got this thing going straight to pin 1 of the ECC85, and that was also fine. And the result is that you get something like this. You've actually painted in what you have been able to check. And that is everywhere that the B+, the supply, goes to. So I'm confident now that I've got my supply going to where it's supposed to go. And I actually went one step further. Since I was replacing these electrolytics, I also replaced the cathode bypass capacitor on the ECL86. And so once we've checked all that, and we know that the supply lines are getting to where they're supposed to get to, we can now start looking at the next stage, which is the audio stage, which is what I'm going to do next. When I talk about the audio stage, what I'm talking about is from where the audio goes into the system, whether it be from an external source like this TA or TB, which is the tape or phono, or from the radio stages, be it FM or one of the AM bands. So from that point onwards, all the way through till it comes out of the speaker. That's my audio stage. And in this particular case, it's sort of this over here, okay? So let's actually go to the end here first. We've got the secondary of the output transformer. It feeds a speaker, and it's actually connected to ground on one side, and the other side is the speaker positive, if you want to call it that. There's also a connection to an external speaker connector or speaker socket, which we saw on the outside. It says 3 ohms. That's very low. But anyway, if we go back, we've got the primary. Now, let's look at what we've got to be worried about here. We have a capacitor across, literally across this primary, and that is 3.3 nanofarads. Now this capacitor, it's got 2 dots over there. So what voltage rating is it expecting? It's this one over here. It's 400 volts. You see those 2 dots? I think they're dots, not squares. No, they actually seem to be little squares. So I think it's that one, 500 volts. And that means that we need a fairly high voltage capacity. And the reason for that is, although the supply is like 200 and something volts, there it is down there, 280. When you've got an inductor, which is the case of a primary of a transformer, the voltage can actually soar up. And that's why these capacitors should always be fairly high rated. I normally put in about 1,000 volts, but if I don't think I've got 1,000 volts in 3.3 nanofarad. I think I'm going to replace that with a 630. No problem, 630 volts. So that capacitor sometimes goes dead, very often goes dead, especially in the older radios. This radio's got a different type or it's got a different type of capacitors. So I'm not sure that we're going to have the same problem as we had with the normal paper caps of old, but I'll check anyway. But that is there to stop oscillations and to cut off some of the extremely high frequencies which this transformer won't pass through anyway, and your speaker wouldn't be able to handle it all. But that is where that's being driven by the anode of this pentode on the ECL86. So this pushes the signal through that primary, which then induces it on the secondary, and the speaker gives it to you, and you get it into your ears. Okay, now, what do we have here? We've got a very, very simple setup with this pentode. We've got the grid receives a signal, and it is biased. It's cathode biased with a 180 ohm resistor. And again, it is wire wound. It's got the cathode bypass capacitor, which serves as a short for AC and gives you better gain. But that's the capacitor I've changed. And that resistor is easy to measure. You just go to pin 7 and ground. You should get about 180 ohms. Then we've got this grid stopper 100K and a grid leak 1 meg, and we've got this capacitor here. Now this capacitor is very important because if this capacitor leaks DC voltage, if it's leaking, then it'll take the B plus over there, it'll take that voltage, which is fairly high. I don't see it noted anywhere, but it's usually about 20 volts less than that one. So it's probably in the 250, 260 volt range. And if DC can get through, it'll bias that positive, which you don't want. You want this thing to be at 0 volts, and it will be at 0 volts if this is a complete DC block, because there's your ground. There's no current going into the grid because it's a very high impedance input. So no current, no voltage drop. So if that's 0, that's 0. And then that becomes a positive voltage because current is flowing through that resistor, and that gives you a negative voltage when you look at the difference between the grid and the cathode. It's cathode bias. That's how it works. Once again, I go into a lot of detail in the back to basics, so you can go look at that as well. But it's very easy to check these components. The one that I'm worried about is this guy over here, because I need to make sure that it's not leaking before I power the radio on. I don't want to blow this tube. This is a very valuable tube, so we have to be careful. Now, what else does it do? Well, it takes the audio from there. And that is, what is that? That's just the preamp. That's the output of the preamplifying stage, the triode that preamplifies the audio, feeds it in there. There's the load resistor to the B+, 220K, and the audio comes from there and gets fed into the grid of the power section to be amplified. But what actually comes in here? Well, here we've got a similar situation actually. We've got a 100 ohm to ground, but now we've got this thing here. And what is that? That's going back to the transformer, to the output, to the speaker. Why would we take the speaker signal and feed it back to there? Well, this is called feedback. In this case, negative feedback. It actually affects the tone that gets through and gets amplified, because what happens is if you've got certain frequencies that are allowed to go through here. Now, which frequencies would be allowed? Well, let's see. If we take the signal from here, all frequencies go through a resistor, but higher frequencies go through a capacitor. And so that means that although all frequencies are attenuated or resisted by this resistor, because there's a wider path for high frequencies, not necessarily very high, just higher frequencies, it means that the signal that's here is that one, but high frequency rich, okay? So it's basically the treble is being fed through there and gets summed to there. Now what it does is it actually subtracts. If you look at how a triode works, whatever signal you have here will be subtracted from that one. So this thing is giving us a path for the feedback path to reduce treble on the output, okay? Again, back to basics. And here we've got a grid leak resistor, 10 meg, very high. The whole tube is practically being biased by the leakage, the very low leakage from the grid of this triode through that 10 meg. That 100 ohm resistor is more as an excuse to give us a path for feedback. So although this is sort of cathode biased, it's actually more grid leak biased. Then we've got this capacitor, and another one. This is another one that's as important as that one. This one here, again, if that is leaking DC, you could have problems with your biasing of that triode. But this is where the audio goes in. This is the potentiometer, and the pot is the main sort of doorway for the audio. So if I can check that audio gets through here and gets out the speakers, I'm happy. But I want to go a bit further back, because I actually want to use this socket as my input signal to test the audio stage. So very, very briefly, let me just show you what happens to the audio before it gets sent to the preamplifier, before it gets to there, okay? What do we have here? We've got, where does it come in? That's where it comes in. There, it comes in from here. Now, there is, what is that? That is shorting it to ground. What is 2C and B? Ah, this is clever. C and B is the off switch. And what it does is when you hit the off switch, it shorts the audio to ground, which means that because the system's still got a bit of power, there's still voltage in the capacitors, charge in the capacitors, it could sort of carry on playing. And what they do is, no, they say, right, you want to switch off, we'll cut off the audio, regardless of how much power the radio's still got. So it shorts the input of the audio to ground. So your radio goes immediately silenced the minute you push the off switch, the aus, okay? So that is a silencer, a mute. But other than that, when it's on, you get this situation here. Audio's coming from here, which is through that capacitor. Through that capacitor, and there's a short there. That is 4C and D. What is 4 again? 4 is bass. Okay, so you want to give it more bass. I think that's bass and voice sort of thing. So depending on how that switch is set, your audio is either going straight through or it's being filtered through a capacitor, which means that your bass is being reduced. Remember, bass frequencies, low frequencies, have a problem getting through a capacitor, so that if you don't select bass, the sound that's going to go into your potentiometer is going to be bass poor. It's going to be more trebly, more voice, I suppose. So that is that. So the audio is still coming in here, and it comes from there, and it comes from there. In fact, it goes to there. Okay, 1 and 4, let's see, it should say that here. 1 and 2 is the Outnahme. So 1 and 2 is your tape out. So whatever signal is there goes through a 2.2 meg to there, and you can take that to an external tape recorder. We're not interested in that. We're interested in the input, 5, 3, and 2. So this is the tape in, or this is what I call phono in. Okay, they call it tape in. So your signal comes from here through a 180k resistor, just to basically get at the same level as the audio coming from the radio. Goes to there, and depending on whether you've got tape, if you do have TA selected, it goes in there, and then it goes into your audio chain. Okay, what is this line over here? Boy, they really go a long way to get rid of treble. Oh, this is your bass treble control. Okay, so they've taken the input of the audio. This is where the actual audio is going to come in, the first point of entry of your audio. They've taken that and they've put it through a capacitor, and there's a potentiometer to ground. So if you have your potentiometer all the way that way, it means that this capacitor is directly to ground, which means it'll cut out high frequencies, so it's getting more bass. If it's the other way, what happens to the other way? The other way takes a signal from there, which means that you're cutting down your bass. This is the usual system of theirs, where they've got a multi-section potentiometer, and this is the pseudo loudness. It sort of changes the tone, changes the characteristics of your signal, so it changes the tone depending on where your volume control is. So that gives you more bass at lower volumes. As I said, I've gone into this so many times in the Back to Basics series and other series. I'm not going to explain all that. But what I'm going to do is I'm going to check everything that I can check in this section of the circuit that I've just described. And hopefully when we've done that, we can actually feed a signal in here, power this up very carefully, and we should hear the tone coming out there, the audio coming out there. And the beauty of this, in this particular radio, is that all we have to put in is one tube. Normally we have to put in two. In this particular case, we put in one tube, this ECL86, and it acts as audio preamp and power amp in one, and we should have music. All right, let me do that, and I'll show you if I find anything wrong with these components, and then we can test it. I want to check the state of these capacitors, because these are not paper caps, they're film caps, so I don't really know whether they need changing or not. I'm starting with that 3.3 nanofarad 500 volt capacitor that goes across the primary of the output transformer. It's sitting over here, and I've lifted the one leg, the one at the back here, so desoldered that. It's completely floating. And then I've connected my leads for the capacitor leakage tester across the two. Now remember, the leakage tester is floating, so the voltage will not get to the radio at all. All right, I've got this on the low range. I've got it off, and I'm going to switch it on. Now this is going to produce a voltage that's completely floating, which is what we want. And let me put the voltage up to about 100 volts. Yep. And now I'm going to turn this to the 100 milliamp range. I've got this at zero current, 100 milliamp range, and I see no flicker. I'm going to the 10 milliamp range, still no flicker of current. 1 milliamp range, still no flicker of current. Let's step this up to the limit. This is as far as I can go on the low range. I'm going to drop it down a bit and then put it on high. And now I can go to the limit. And because this is a 500 volt cap, I can go all the way to 330, which is the limit of my meter. And it's giving me about 1 microamp. Now that seems pretty good to me. That actually seems very good to me. So let me put that off. And when I put that off, it discharges the capacitor. I want to try a new capacitor and see what we get. This is a 3.3 nanofarad, 630 volts, and I'm going to switch it on there. All the way to 100 microamps, I get absolutely no leakage whatsoever. I see no flicker at all on the meter. But slight difference between that and the original cap, the 1 microamp. But 1 microamp to me is not leakage. I think I'm going to leave it. that capacitor is staying in place. Okay, good. That one's tested. Now I'm going to test the other capacitor, the one that links to the grid of the output power section. And this is that 6.8 nanofarads that I said is dangerous if it leaks because it can blow the tube. I've lifted one leg, obviously. I want this whole thing to be floating because the supply is floating. It'll float completely and it won't connect 300 volts to parts of the radio that shouldn't get it. Let's see what we get here. Okay, so let's put it on the high range, switch it on to 100 milliamp range, no leakage. 10 milliamps, no leakage. Let's put the voltage up. I'll put up to the max. This is also a high voltage capacitor. No leakage. 1 milliamp, no leakage. 100 microamps. I'm seeing about 1.5, 2 microamps. If I put a new cap in there, I'll get 0, but 2 microamps on there, I'm not worried about it. I'm going to leave this as is. These capacitors are proving to be quite good. So this type of capacitor is proving to be quite good. Now, most of the film caps are of this type. So one can sort of assume, I know that's the wrong thing to do, but you can almost assume that they're all going to behave similarly, which makes our life a lot easier. And I will check the others, but at least I'm not going to have to replace a hell of a lot of capacitors. This has really simplified matters. I'm going to check the remainder of the circuit, and then I think we'll be ready to power it up. I obviously have to solder those 2 capacitors back. I've now put the audio tube, the ECL86, in there, and I'm ready to give it a shot. We'll just select TA, which is the 3rd button. So the minute I put power on the dim bulb, we should have this thing powered on. I've also got a speaker on there, and I've got the multimeter ready to monitor B+. Okay, the Variac's on 230 volts. I've got this on maximum restriction, so I've only got one bulb on here. We look at the bulb and it should go on as we turn on, and then it should go down as the capacitor is charged. Let's make sure that everything is off. Okay, and let's go. Whoa, that's not good. That's not good at all. That was a dead short. Bloody hell, that should have gone down. That thing just went totally bright. I think we've got a short in here. Damn. Well, it's not really a dead short because this did build up a bit of B+. Not much, but if it was a dead short, we'd get 0 over there. Well. I'm beginning to wonder if it's the transformer, because this transformer's got a lot of dark staining on there, which is not unusual, but it could be an indication of something seriously wrong. I want to make sure it's not the tube, so I've removed the tube and I'm measuring the voltage, the B+ there again. Let's see what we get now. Okay, let's do it again. Oh, no. Still something wrong. Far too bright. So what are we facing here? You see what I mean about it being dark? It looks like it could be burnt, so we could have a short inside the transformer. The first thing I'm going to do is I'm going to remove the secondary from the bridge rectifier, because that could be the cause of the problem. If I switch on and I still have a short, then it's probably the transformer. There's also the heater winding, which could be shorted, but we'll take it one step at a time. First, let's check this section. Okay, I've disconnected or desoldered the secondary wires from the bridge rectifier. They're floating here. You've got to be careful because this will be live. So let's see what we get when we switch on now. Let's have a look. Oh, brilliant. That is brilliant. That's great. No more shorts. This means that our short is either here or here to forward, because I'm not getting a short when I remove that secondary from there. Now, I just want to test to see what voltage I do get on the secondary of the transformer. Got to be very careful because there's high voltage here, or we hope there is. Now we set the meter to AC volts. Yep, we're getting a high voltage. Near 240, that sounds about right. And the other thing I've noticed is that one of the dial lights is on. The other one is burnt out, it's darkened. So one is on, so our heater supply is working as well. And we've got a problem with the rectifier. So I was going to replace that with my MOSFET adjustable one anyway. It just means I have to do it sooner. And that's what I'll do next, and we'll test it again. It could still be something after the rectifier. We'll just have to test it and see. I've replaced the selenium rectifier with a MOSFET dropper. Let me show you what we have here. I 3D printed this little cover because I don't want live voltage over there. So this is what we've got. The secondary supply from the transformer goes in there and there. And there's our ground, which is soldered to the chassis over here, just as it was before. And there's our positive going to the first filter capacitor. Now, I did this project, and I will link a video to this. You can go and check it out yourself. But basically what this has is 4 diodes, 1N4007s over here. It's got a MOSFET here, and this MOSFET is used to create a voltage drop. Because the selenium rectifier has a much higher voltage drop once it rectifies than the silicon diodes, this thing helps you to adjust it, and you can literally adjust the drop to get the right voltage that you want by adjusting this trimmer. And I've shown it working. I've used it before. It works very well. And I created this little cover so we don't have mains voltages or high voltages visible all over the place. Now, what I've done is I've actually put the valve in, and I want to test this. Now, once again, all I'm interested in now is to check what happens when I switch on the power over here. I've got the same single light bulb. I've got the pickup button selected, so when I hit the power, we'll see if there's a problem downside of the rectifier. So, okay, here goes. Ha! Brilliant. You see that flashed? Because that's when the capacitors charge up, and then as the current reduces, it came down. And now, because I've got the tube in there, we should see the current draw increase as the tube starts to conduct. You see that? It's starting to glow. That's perfectly fine. That means the power tube, it's the preamp and the power pentode, are now conducting more current. So we've got 110 milliamps, and the voltage, because of that drop on the light, the voltage the radio is seeing is 181 volts. So it's still pretty safe. Now I want to see if this thing produces audio. So what I've set up here is I've sent a 1 kilohertz 100 millivolt RMS sine into the TA input over there at the back. I've got the volume on 0. I've got this on pickup or TA. And if we look at it on the scope, let's see what happens. I've got this connected to the bench speakers and also the scope. Ah, brilliant. The volume pot is dirty. I can hear the scratchy. Whoa. Some oscillation going on here. It is oscillating. So we've still got a bit of a problem here. But let me put the tone off so we don't have to listen to it. Let's see if it still oscillates. Yeah. Oi. It really goes nuts. It's over a certain amplitude. This thing's starting to oscillate. And that could be, well, let's see if it's something to do with the tone control. The tone is doing some weird stuff here. I've got to check all those tone shaping connections on there. I've got to make sure the feedback's in place because something weird is going on here. Now this is a 1 kilohertz tone. Let me change that to, say, 300 hertz. It's even oscillating more, or it's oscillating sooner. See that? Just wiggle the tube. No, it's got nothing to do with that. Ah, we've got a bit of a mystery. Now here's the tone control, and it's doing some weird stuff. This tone control is really strange because it should only work, it should be more bass one side, more treble the other side. On 300 hertz, it should be affecting the bass frequencies. Let's try 2 kilohertz. Oh, my socket here is weird. That's better. Okay, what have we got here? No, still oscillating. That's 300 Hertz. Let's try 2 kilohertz. It's oscillating. Okay. And we can see here that at 2 kilohertz, if we choose more bass, our treble gets attenuated, and it should work the other way with the bass frequencies over there. All right, we've still got a mystery to solve. Mind you, with the way this radio was, I'm really not surprised. Let me give it some more thought. Actually, before I do that, let me see what voltage we're getting. I'm going to increase or decrease the resistance by giving it 2 bulbs, actually 3 bulbs. So we've got, what is that, 140 watts over there. This could be all sorts of things. I'm going to try a different tube in there because it could be the tube. Let me put that off. But what I want to do here is I want to set the voltage that it's supposed to be seeing, more or less. I know this is not going to be the exact final voltage because all the other tubes are out, but the main one is that power tube. So I can actually sort of adjust the voltage more or less to what I want, and I'll do that first. Now, according to our schematic, it says we should have 282 volts. What I'm going to do is I'm going to bypass the dim bulb limiter, so it's seeing the full, what is that, 230 volts, and I'm seeing 300. Now I need to reduce this. It's actually quite a big drop. $282 is what I want. Actually, I'm going to leave it at 280 for now. See that? Brilliant. It works well. Now dialing it in exactly is not an issue because your main supply is going to change as well. So this is only dialing in the drop in voltage, a percentage that you're taking off by dissipating the heat of that voltage across the MOSFET. The MOSFET's really acting sort of as a variable resistor to effectively raise the ground, and it gives you a reduced voltage. So what you can see here is we've got ourselves 279 volts. The schematic says 282 and on FM 275. This is going to alter again. I'll be changing this at the end, setting at the end when all the tubes are in. I'm being optimistic and everything's working quite well. Okay. All right, folks. I've just gone through the wildest wild goose chase I've ever been involved in, trying to sort out that crazy waveform that we're getting on the output here. First of all, I've got to clarify something. That waveform that you were seeing was not really completely in oscillation. That was just the breakup. The whole thing was just breaking up at one point, and we were getting clipping and all sorts of stuff going on. There was actually an oscillation at some point, which I managed to recreate because I was trying to chase down what the hell was going on here. And that oscillation was at about 17 kilohertz, which means that it was at the speaker, but you wouldn't hear it, but you could see it on the scope. Now, I got to tell you, this is a real duh moment. Mind you, it's a duh moment that is 24 hours after I started this chase. I found the problem, but before I tell you what the problem was, and before you realize just how stupid your host is, I'm going to tell you where I went looking for the solution. So, one of the first things I did is I thought perhaps it was the supply. Perhaps there was not enough decoupling to the triode section of the supply, and that uses a 10 microfarad capacitor, the high voltage 10 microfarad capacitor. So I replaced that, and in fact, I put it on the underside so it wouldn't go past. It was actually quite close to a cable or wire, a screened cable, going from the pot to the input of the triode, which is where the audio is, right? So I put it on the underside. It's a small cap. It fits here. But before I put it back, I replaced it with a 47 microfarad capacitor, thinking more smoothing, perhaps that could be issue. It wasn't the issue. So that cap was the first thing I investigated and found there was nothing wrong with it. And then I thought of looking at the grid stopper, which is actually there to prevent oscillations. And I found that that wasn't the issue either. I increased it, decreased it. It involved removing the capacitor, the resistor from the back and changing the values. Nothing changed. It was exactly the same. So I then took the next step, which was to replace the 3 capacitors that I thought were in good condition. That 3.3 nanofarad across the primary, that could be one. That's also got to do with oscillations. Nothing changed. Then I went and replaced the one that feeds the grid of the pentode, but nothing changed. So I went back and replaced the one that feeds the grid of the triode. And guess what? Nothing changed. Now you can see this whole section, the entire section here, has been painted in a different shade of green. And this shade of green is all the checking that I did after I had the problem with the signal to where I am now. Everything was checked. Every component was checked. I desoldered a hell of a lot of stuff. I lifted a hell of a lot of stuff. Some of them you can measure in the circuit. Some of them you've got to remove one leg of. Everything was checked. And the problem just carried on and carried on and carried on. So I thought, okay, the pentode is biased with a 180 ohm resistor. Let me play with that value. I increased that, I decreased that, I did all sorts of things to that and found it did nothing to the signal, so I left it in place. Then I thought, okay, let's check the biasing of the triode. And the biasing of the triode is actually this 10 mega ohm resistor. And if this thing was increasing or giving me too great deviation to the point where it clips, that could be the reason. So I played with that. I decreased it to 5 meg. I increased it to 20 meg. Nothing happened. So then I thought, what about the cathode resistor? And I altered that around a lot as well. And I got to the point where if I put a 300 ohm resistor in there, it sort of decreased a bit. But then I realized because the feedback is coming back through that or into that, I would have to change the feedback circuit as well. By the way, those components are all fine as well, and I didn't change any of that. I played around with all the components in the potentiometer circuit, and I was getting completely desperate here. At that point, I thought the problem must be the output transformer. I figured that maybe they used the wrong transformer. Maybe they had spare transformers from previous versions, and this is the ECL86, the pentode of the ECL86. It's supposed to be very, very similar to the EL84 that was used on previous models. Maybe they just used the transformer because they had it. And I thought, okay, well, how do I change the characteristics of the transformer? And what would that do? Well, basically what that does is it takes the impedance on this side, on the secondary, and it multiplies it by the square of the turns ratio. So if you've got like 4 ohms here, right? If you've got a 4 ohm load on this side, on the primary, it's going to show, let's call it, I don't know, 1500 ohms, right? At the impedance. If you take 8 ohms, that's going to become more than that. That's going to become 3000 ohms. So the way to play with that, the way to check what the characteristics should be, is by changing the load. And I put a whole lot of resistors across here. I put a 4 ohm, or rather I put 8 ohm. Then I put a 4 ohm. Then I put a 3 ohm. Then I went as high as 16 ohm, and nothing was changing. And while I was checking all this out, I noticed something. And this is where the climax of the story comes in. And this is where I bow my head in shame, and I have to restate that old adage that when you assume, you make an ass of, well, in this case, of me, because I found the problem. And the problem is now gone. A little bit more suspense. Let me show you what it looks like now. I've got the same signal going in there. I've selected TA over there, and the volume is on 0. Let me show you the scope. Put the volume up. I'm going to put the speaker on dummy load because this is going to get loud. See that? That is starting to clip at the bottom, which is perfectly normal, and at the top. Okay, I've got a fairly strong signal coming in, but if I take it to just before clipping, I've got 3.17 volts RMS, and there's absolutely no jumping around. The clipping is perfectly normal. See that? That is what I wanted from the start, and I've got to play with I can play with the tone control. This is a 1 kilohertz tone, so it will affect it when I choose bass, more bass. It attenuates the signal. When I put more treble, it just gives it a little bit more. That is perfect. That is working. Bloody hell, it's working beautifully. So what the hell was the problem? Well, as I said, never assume anything. Let me show you what I did wrong. Tell me what's wrong with this picture. I've got a black wire to the speaker. I've got a blue-green wire to the speaker. Naturally, you would assume, or I would assume, and did assume, that the black was the ground. And I know that the speaker is connected on one side to the chassis. So this I took as ground. This I took as the other lead of the output transformer to the speaker. That was wrong. These guys have wired this thing up in a way that can only be to make people like me make fools of themselves. They've wired this the other way around. This is the chassis connection. And the way I found that out was I was looking at the output transformer and where it connects to what. And I noticed the black guy, no, there it is. That black guy there goes to the signal. This one here goes to this wire, which is bolted to ground. Now, I don't know if somebody's played with this. They may have changed this around because this soldering here is a little bit weird. This thing just goes to the shield on the bottom of the radio just to protect it from noise. But someone may have changed this around. I don't think, in fact, I think that is the ground connection on there. I'm not sure anymore on these DIN sockets. But they may have changed this around and this was not the way it came out of factory. But seriously, I didn't even look at that. I just assumed that black was ground, which means chassis. And why does it give us all that strange waveforms? Because I'm using two systems of ground over here. My signal coming in here has a ground. This comes from the signal generator. Now, the signal generator ground is the same as mains earth ground, okay? Now, if that's all I did, if I had not connected anything else to this, and I didn't try to look at the signal, it would have sounded fine on the speakers. It would have, because the only reason I had a problem is because I've got my oscilloscope on the output, on the speaker, across the speaker, and this guy goes to what I call the speaker's ground. So these two grounds have to be the same. This ground from the scope is also connected to effectively mains earth. So this guy is connected to the input, to the signal coming in's ground. And what I was doing effectively was I was shorting the other leg of the speaker to ground, to the earth ground, and I was monitoring a strange signal on what I thought was the positive. I was monitoring effectively a signal across that feedback network. I think that's the only explanation I can find. And that is my problem. This one of the most basic, stupid things one can do. And you now have proof that I have done it. And that, my friends, is where I'm going to leave you for today. I've got quite a bit to do, trying to find a condenser that'll fit on there, trying to fit it on there, seeing if I can get the dial cords working and everything else, but I'll do that in the next video. This one could probably be finished in 2 videos. We'll see. And for now, I've got some presents to buy and all sorts of stuff to prepare for Christmas. And I want to wish you all a Merry Christmas if you celebrate it, and enjoy the time with the family. And I will see you soon after that with the second installment. So if you've enjoyed this, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon, PayPal. Links on the description below. Once again, thanks for watching. Bye for now. And most of all, stay safe.